In this video, I'd like to apply what we know about sums so far to the area problem. That is, finding the area under the function y equals f of x on the interval from a to b. Here I have a function that is positive, so I really am thinking about the area under the curve, although everything I'm getting ready to say would also apply to that case where part of my curve was below and some of my rectangles just had a negative height, and therefore we'd think of the area as being a negative as well. Well, if we think about what we've done before to approximate the area under the curve, we would first divide the x-axis into n subintervals. I don't know what n is, but just imagine as being some amount of, x values between a and b. We usually think about our subintervals being equally spaced, but I didn't draw that here, because all that I really know about them is that there's some number of x values chopping up the x-axis. And I could think about that first x value, a, but I want to give it another name. I'm going to call it x sub 0, because I want this first one here to be x sub 1. And the next x value after that can be x sub 2. And by calling this one x sub 0, it kind of fits in with the rest of them. And then I just have a list of x values where I'm chopping up my x-axis. And this one here would be the n minus first. And the last one would be b, but again, to kind of make it fit in, I'll call it x sub n. So when I say subdivide the x-axis into subintervals, this is really what I mean, right? We're choosing x values and chopping up the x-axis with them. This list of x values has a name. It's called a partition. When we chop up the x-axis, we're partitioning the x-axis. Each subinterval has a width. We're calling that delta x sub k. If my rectangles all had the same width, then this would be that calculation b minus a all over n. But right now, some of them are wider. So on the first subinterval, this is delta x sub 1. On the second subinterval, it's delta x sub 2. And what I notice is the right-hand endpoint, that x values subscript tells me which interval I'm on. So the first subinterval ends in x sub 1. The second subinterval ends in x sub 2. And so on. The kth subinterval would end in x sub k. But this just represents that width. On each subinterval, I need to pick a point, a sample point. I'm going to call that ck. So on the first one, this little red value would be c1, and then c2, and it can be any point I want it to be. It doesn't have to be any point in particular, just one on each subinterval. So I just pick those. Now, it is common for us in this course to maybe fall back on some things we've done. We might pick the c's so that we have an upper sum. Those are x values that will correspond to a max. We might pick them so we have a lower sum. We might just pick the ones on the right-hand endpoints, or the left-hand endpoints, and then we might have, in fact, picked the midpoints. Or we could just let it be some random number. Now, just so you know, in calculation in this class, we do tend to choose the right-handed endpoints. Then on each subinterval, we construct a rectangle with width delta x sub k and height f of ck. So f of c1 is a function value. There's my height, and I get a rectangle. Just drawing this very familiar picture, imagining plugging in the chosen x values on each subinterval to get a height and draw a rectangle. Each one of these rectangles has an area. I add those up, and that should approximate the area under my curve. And what I can write now to approximate the area, well, on each interval, I have an area that looks like this, and I need to add those together. So this is a sum from k equals 1 to n. F of ck delta x sub k. This sum would be my area approximation. This kind of sum has a name. It's called a Riemann sum. Named after a very famous mathematician, Riemann. There's actually a very famous problem named after him called the Riemann hypothesis. It doesn't have anything to do with what we're doing here, but the Riemann hypothesis is a worthy Google if you get bored. The Riemann sum here for a positive function would talk about area under the curve. It would be an approximation of area under a curve. If my function were to dip below the x-axis, then the sum could actually work out to be negative, and that could be that case where I'm thinking about displacement rather than total distance traveled. But we have one more thing to do. This kind of implies that my Riemann sum would give me an area approximation, that the area is about equal to, approximately equal to, this sum. Well, then we ask ourselves, how do we make this approximation better? And the answer was always to make n larger. Well, then it stands to reason that we want n to go to infinity, that we want to imagine letting n be as large as it possibly can be. And if this limit exists, then this would or should be the true area under the curve. The limit, as n approaches infinity, of this finite sum, this Riemann sum. Okay, so that's what we're going to do in the next video. We're actually going to create a Riemann sum. We're going to use what we know about sums to make that a formula just on the variable n, and we're going to take a limit as n approaches infinity. But before we finish, just a few more notes. If we use subintervals of equal width, then instead of delta x sub k, we could just say delta x. And then that would be the calculation b minus a all over n. All right, so my Riemann sum would start to look like this, right? Still with some ck in the middle. And then maybe instead of just using random points or midpoints, we use right-hand endpoints. Well, there actually is a nice way to write that down if we think about it, because my x-axis would start at a, and then delta x is the width of a subinterval, so the next part and the next point in my partition would be a plus 1 delta x, right? Because that's the width. A plus the width gives me that next endpoint. Well, to get to the next endpoint, I add delta x again, so that would be a plus 2 delta x. And so I just repeat adding delta x to get from one endpoint to the next. So to get to the kth endpoint, I would have started at a and had to add delta x k times. So a right-hand endpoint would always follow the formula a plus k times delta x. And I usually just think about it like that, but we could go one step further and think about it as a plus k times b minus a all over n. And then I could write down my formula for Riemann sum with this in place of ck and with this in place of delta x. And that would look something like this. A sum from k equals 1 to n of f of, and my formula for the right-handed endpoint on the inside of the function times delta x. Given a value for n, this would approximate the area under a curve. Letting n go to infinity, I should find the actual area. We'll do an example in the next video.